Okay, welcome to the last lecture for the Neural Network Architecture Seminar at the Towards AI Discord server. Today we are going to look at the fascinating world of network architecture search. In particular, we are going to talk about some generalities about the network architecture search as a search problem, how the space and the operators and optimizers work. Then we are going to discuss a very popular paper of the 2000s called NEAT that uses genetic algorithms to find neural networks architectures. We are going to talk about network compression, or the more funky name that people use for it, knowledge distillation. And we're going to finish with GDAS, which is a gradient search algorithm for neural network architectures that can be run on modest hardware. When we think about network architecture search, well, this is a search space that is very big. Yes, we are talking about the space of all possible neural network architectures. Of course, this falls into the realm of what is called AutoML, of doing machine learning in completely automatic manners. Yeah, and it is fascinating that people will try to tackle such a search in a space of that size. Yeah. Interestingly, I mean, multiple options exist for, like in any other search problem. Of course, you can try to compute gradients. Yes, you are here not computing gradients over errors, but you are computing gradients over variations of a neural network architecture. Yeah, and we will discuss that a little later. You can also try to do stochastic search, of which genetic algorithm is an example, and we will talk about it in detail too in this lecture. Something that I found fascinating from studying this survey from 2019, a recent survey that is actually very good, I highly recommend it, is that random search. Just make an architecture at random and find which one works better is curiously performant. So hold that thought from this lecture, that if in some moment you need to do a search for neural network architectures, you might be perfectly fine just not doing any of these complicated gradients of stochastic search and just making architectures at random. Two other things that have been used in the field are reinforcement learning and Bayesian optimization. Bayesian optimization was quite popular up till 2013, where it even produce architectures that rival human capability. These days is no longer used as a neural network architecture search technique, and is mostly confined for hyperparameter tuning. And I will not be saying anything about reinforcement learning today. Okay, so that's for the search strategies. Yes, you have the neural network architecture search. There is a way to search, and then there is all the possible states over which we are searching. Yes. Of course, we can search over all possible network architectures. And again, as we said before, that space is just intractable. Yeah. So we can restrict them to try to have a chance to find a solution. And by restricting them, we are adding human bias. We believe that a good solution to this problem we are trying to solve with this neural network architecture should have a certain look. Yes, if we are lucky and we have enough understanding about the domain that this structure that we are trying to use is good, then this human bias we are introducing will speed up the search and lead to a good solution. On the other hand, if we add this bias and the solution is not within these restricted architectures, then we will not be able to solve the problem. So when we restrict things, we better be right. Yes. So the most simpler way of restricting is to make chain structure neural nets, where one layer, we're just stacking one layer after another, and the type of parameters we are searching are the maximum number of layers, the type of layers, and other hyperparameters. This is similar to the type of search you might do by hand when you are trying to find a neural network architecture and you believe it's going to be a multi-layer perceptron. From chain structure neural nets, you can go to multi-branch networks where you can use skip connections, yes, and the input to a layer then is a function involving previous layers, yes. So this captures, of course, chain structures, but also capture residual networks, yes, previously some values, yes, and then dense nets, basically using previous networks concatenated. Finally, we can also do what is called motif search, where we are trying to build automatically a cell or a building block of a larger architecture that then will be repeated in a way that is already prescribed. Yeah. If we go back to the lecture where we were seeing AlexNet, CNNs over ImageNet, yeah, all those systems have a certain cell that gets repeated in a deep network. Yeah. So we have normal cells, reduction cells, transfer cells, yes. And what the system is trying to do is to learn that cell structure and then just repeat it, or learn different cell structures and then do a second network architecture search using these cells rather than neurons. So that's for search spaces. The last thing, once we have a search space, we have a search strategy, is how we compute an evaluation metric. How do we get an idea about how good is a particular solution? In this case, a neural network architecture. So the simple way is to evaluate the full proposed architecture as we will normally evaluate a neural network. Yes, we train it on some trained data and we evaluate it in some unseen data. This is a very, very slow process. We're talking about thousands of GPU days to do that. And instead, what people do is to do approximations. Yeah, and we can do lower fidelity estimates. Yeah, we, for example, use less amount of data. Yes, we take a sample of the data and things like that. We can do learning curve extrapolation. We train a few epochs and then we draw a line and say, well, given how this network is trained, most probably we'll get to this performance. We can also start training, reusing weights from other networks that we have already trained. Yes, for that we need to compute network isomorphisms. We need to be able to say, well, this weight here is equivalent to this weight in this other network, which can be very difficult for neural nets, and we will discuss that in depth when we see NEAT. Yeah. Another technique that is quite interesting as an approximation is to make a big architecture where all the architectures we are interested will be subgraph of this big architecture. Yes, we call this a supergraph. Yeah, and then we will train this supergraph using training data and compute weight for this whole supergraph. So when we want to evaluate as an architecture being a subgraph from this supergraph, we can start training from the weights in the supergraph, or we can just use those weights directly and evaluate there. Okay, so that's give us basically the the main component for network architecture search. Something to take into account is that if you want to compute gradients, you cannot do that over an architecture as such, because the architecture is non-continuous. Yes, you put a neuron there or you don't put it. Yes, you use ReLUs activation functions or you use logistics. So are binary decisions that don't give you things over which you can compute derivatives. Yes, you need to make the problem continuous, and the solution that people normally use that is to make a convex combination of all the operations that can be done. For example, if you have the choice of activation function, a ReLU or a sigmoid, yeah? Instead of saying you need to choose between these two, we do, we say we have an alpha that is between 0 and 1 times the output of the ReLU plus 1 minus alpha times the output of the logistic, and then we are searching in the space of this alpha parameter. That type of decision is continuous, and you can compute derivatives of that. Another topic to keep in mind is that most of the network architecture search to date has focused on image classification. So network architecture search on things like network architecture search on transformer, for example, it might not be a topic that is so well studied. Something else also to take into account is that the stochastic, evolutionary, genetic algorithms have a very, very long history in the field of network architecture search, and the algorithm we are going to see next, NEAT, not only does network architecture search, but it also a way to train the weights, yes? So that's no longer happening these days. People no longer use genetic algorithms to do weight optimization. It just takes too long and is not efficient enough for the very large networks we are working on. Everybody uses stochastic gradient descent, as we have seen all throughout the lectures. But the beauty of the evolutionary algorithms is that they produce smaller models than other techniques, and we will discuss why. Network compression or knowledge distillation is related to network architecture search, and that's why I have included in this lecture. As I mentioned, Bayesian systems are no longer used or are no longer as popular as before. So the NEAT paper is something that for a paper from 2002 is fascinating how much it captures the attention of people, particularly newcomers to the field. The paper is called New Evolution of Augmented Topologies, yes, and as I mentioned, learn weights and network concurrently, and start small and protect solutions through a technical speciation. And the issues it addresses is being able to do mixing over architectures, what is called crossover in genetic algorithms, and handling, allowing new architectures that have unoptimized weights to improve its weights before comparing them with other architectures through this process of speciation. The other beauty about the algorithm is that it minimizes the size of the architecture without requiring a cost function that includes a minimum description length term. If you want to obtain a small solution for something, yes, common technique is to say, what I'm optimizing, I'm adding a regularization term that discounts solutions that are too big. Yeah, and that works really well. The problem is that if you do that, you have to have an idea about how complex should be the solution, so you can penalize solutions that are too big. That requires you to, a priori to know how complex is the solution. But in this case, you really don't know what size of the neural network architecture you are searching. So the fact that NEAT doesn't require this type of regularization, doesn't require this minimum description length term, is a big, big advantage, because it will make the smallest architecture that works well without you needing to come up with a value for that parameter. So architectures are graphs, yes, and as we saw in the graph processing lecture, graph has the problem that they require learning to be permutation invariant, yes. The usual way to do crossover in neural networks, especially in genetic algorithms, involves just taking random things from each of the parents to produce a new instance, yeah. So in this case, yes, we have these two neural networks, and they are actually the same network. It's just that they are numbered differently, yes, and we have different weights there that are captured by different shades of gray. So if you want to make an offspring of that, yeah, if you were just to do it randomly, you will completely destroy this network. So you have two architectures that are the same, and you are trying to blend them together, in which case you wouldn't actually change the architecture at all. You will just change the weights from the blending, yeah? But instead, because these picking nodes randomly from one and the other, you end up completely destroying this and making something that doesn't work at all. How to solve this problem is very hard, because in a simpler system, you will have to compute what is called a graph isomorphism. You have to be able to say, oh, A here is equivalent to C there, etc. And computing those type of matchings is very time consuming, and you will have to do it for every pair of neural network architectures in your population. And so you have a n-squared algorithm on this number of instances, and on top of that, this isomorphism has to take into account all the nodes in the architecture. You can quickly see that that solution doesn't scale at all. Instead, what NEAT does is it assigns global numbers to each of the nodes as they are being created, and global numbers to their connections too, what they call innovation numbers. So the innovation numbers appear here in the gene. So the way NEAT encodes an architecture is by having two lists, a list of nodes and a list of connections. Yes. So the connections themselves, the nodes themselves, are input nodes and output nodes and hidden nodes. Yes. And when the algorithm decides to add an extra node, it receives a unique number in the whole system. So we always know, as architectures get more complex, where these nodes come from. And in the same way, the connections also receive a unique number, these innovation numbers. So we can also tell that two connections are the same because they, in some moment, the ancestry of the system can tell that they came from the same place. So each connection has an input node, an output node, a weight, and whether it's enabled and disabled. Some connections are disabled, which means that they are not active, but they are remaining in the genes because they can be reactivated later on. And as I was saying, the system also learns weights. Something else to take into account here is that this network representation, these phenotypes, allows for cycles. So the system can learn recurrent networks, and indeed it does. So stochastic search through genetic algorithms have two different type of operators. Some operators execute over an instance alone and call it mutations. Yeah. So you have a type of mutation here, for example, that adds a connection. So we are deciding to add a connection between 5 and 3. So we have before 6 different connection genes, and now we have 7, with the 7 being this connection between 3 and 5. That 7 is a unique number, global number, to indicate this new innovation. Alternatively, you can have adding a node type of mutation where we have here a connection between 4 and 3. Yes. So that connection between 4 and 3 that was in gene 3 is now disabled. Yes. And it's disabled because we have replaced by 2 connections, one between 4 and 6 and another between 6 and 4 that receive innovations numbers 8 and 9. Yeah. And we have also incorporated the node number 6. Yeah. And the weights these additional nodes are receiving will be 4 to 6 will be very close to the weight that 4 and 3 was had before, and 6 to 3 will be very close to 0 or a very, very small number. With the intention then that this whole network will behave as close as possible to the original one. So these are for the mutations. The most important thing is how to handle the crossovers. So in the crossover we have 2 parents, yes, and here in the left side we have a parent which is relatively simpler, and another parent on the right side, parent 2, that is more complex. The important thing here is because we have these innovation numbers, we can really tell very quickly which edges and which nodes in each of these different architectures correspond to which one. And therefore, we can say we are going to take these connections from one parent, this connection from the other, yes, and then finish the offspring with connections from the other one, and build this offspring that is inspired by both parents and didn't require any type of isomorphism. It was very, very fast to compute. Yeah, so this is really the big advantage of the algorithm. Now, this algorithm like this will not produce enough variations for the architectures. Why? Because as the system gets to a point where some neural network architecture is good enough, it will be too dominant. Yes, all the population will be taken over by variations of that at the weight level, and the system will just start optimizing the weight level, the weights for that architecture. Because any offsprings produced will have bad weights, so its fitness function, its scoring, will be too low to take over these more established architectures. To avoid that, NEAT uses this idea of speciation. It computes how different the architectures are, and for architectures that are too different, then they are kept in separate pools. And the size of these pools are relative to how good the architecture is. So if the architecture is very good, the pool is going to be big, and he's going to find variations of this big architecture and better weights. But the other variants will still not die and remain in these speciation pools to get better. The paper has a case study where they try to solve the problem of having a cart with 2 inverted poles. Yes, so these are sticks that on top have a weight, and the weights are part of the problem definition. Yes, you have to move the cart left and right to keep the poles from falling. This problem is a simple problem to solve if you have the angular velocities of the poles. But if you don't have the angular velocities of the poles, you only have the actual angle, it is a hard problem. And the beauty of the solution that the network built is that it's a very, very small network, yeah, and it has 2 recurrent connections. Yes, the first recurrent connection that you can see here in I think it's node 13 in this figure, like the center node, yeah, computes the velocity of the angles by doing this recurrent connection on the angles inputs, and from there it has a recurrency at the output, yes, to take into account the speed, to continue moving the cart in one direction once it has decided to go there or not. So with these 2 little recurrences, the system is basically computing the speed of movement and computing the speed of change of the angles. And this type of ingenuity, it's is fascinating because for a human to design this, it will take a very deep understanding of the problem. So the last part that I need to mention is why NEAT produces very small solution is because it starts from absolutely nothing. It starts from a neural network architecture that is just the outputs, the output connected to the inputs. Yes, so it has no layers, no hidden nodes, and by adding more nodes, yes, then it starts growing the solutions. So a good solution that is found, it went through all these smaller solutions before. So we have an expectation that will be the smallest solution possible. And also because everything starts from the same point, then these innovation numbers that describe the different nodes that have been introduced and the connections, makes sense that they will be shared by the whole population. Yes, because the first layers will be most probably shared by all the populations in more complex architectures. So that's for NEAT, and we have quite an active genetic algorithms channel in the Towards AI Discord server. If you want to learn more about it, I'll invite you to join there. The other thing I want to mention about NEAT is the type of the complexity of the algorithm is refreshingly simple in comparison to backpropagation, for example. There is no discussion here, as you have seen, about gradients. There is no discussion about mini batches or loss functions or anything of that sort, which means that mid-high school level of mathematics and reasonable programming skills allow anybody to implement it, and that's a great reason to use it. Yes, because it helps bring more people into the field. Okay, so in terms of network architecture search, this network compression concept is a little different than the other ones, because what we are trying to do here is to capture the knowledge present in a very large system into a smaller neural net. Yes, and the reason this paper has gathered so much attention is because it is an idea that comes about very naturally. You have a system trained and you use that system. The obvious idea is that you use the large system to produce training data that then you feed to the small system. And the truth is that doing that actually doesn't work that well, or doesn't work at all. The beauty of Hinton, Vinyals, and Dean paper from 2015 is that they realized that the information that is in the larger system is not the target class that they produce as output, but the understanding of what are near misses, what are the other classes that were confusing with the class picked. Yes, so basically, instead of having an output to say this class is a car, yeah, what you want to have is a probability distribution. Yes, soft targets, the logits. Yeah, so you want to say this is 80% a car and 60% a garbage truck and 5% a bird. Yes. Why? Because that captures much more useful information for the smaller network to understand the problem structure. the domain, yes. And in that sense, capturing that information by the large network requires a lot of training data. And once that system has been trained and is performing well, then we can profit from this extra information to train the smaller network. If you think about it, when you give training data to a system, you just give them an image that's has a car there and say, this is a car. Yeah. The fact that the trained system can say, well, 80% of the time this is a car, but maybe under certain circumstances with certain lighting, this is a garbage truck and I'm not doing a good job here. Yes, that realization is not present on the original training data on the large system, but is part of the knowledge that the large system have acquired. And a simple way of obtaining this information is to raise the temperature of the softmax function that is used to when obtaining the final output of the large system. And there is a quote about that in the paper about how training against the logits is key. Yes, that it's saying that well, if the comparison model generalizes well, it's because the average large ensemble of different models, the small system will do much better on test data than a small model trained the normal way on the same training data that was used to train the ensemble. Again, because with this information about what are the confounders, the smaller system can gain this knowledge about the domain in a much better way. And in the CNN, in the vision transformers, I believe, we discussed a case where they were using a CNN as the teacher for knowledge distillation and a transformer as the learner. And the learner then, in that particular case, that is very unusual, outperformed than the teacher. And now we're going to close with this neural architecture search using gradients. Most of the techniques in neural architecture search using gradients uses things like 3000 GPU, uses 3000 GPU hours on a small data set. Yeah, so they are really beyond the realm of anything any of us will ever do unless we work for a very, very large organism that have access to that type of hardware. Yeah. But this paper from 2019 uses only 4 hours and have a system that has a test error of 2.82%, only 2.5 million parameters, which are state of the art in 2019. Yes, it is very interesting that they obtain that level of performance with so little computation. Yes. And what they do is to build a differentiable sampler over a directly acyclic graph containing billions of potential architectures. And they build this using stochastic gradient descent over this differentiable architecture sampler. This whole concept, and it's quite hard, and I will give you some ideas about it, but this is a topic of active research, and re-implementing this paper, for example, is quite difficult. I work with somebody on Discord about it, and it has multiple parts that are very difficult to really ground into code, even looking at an existing implementation provided by the others. So the idea here is that you have all these different possibilities of connections between nodes, and all these possibilities are kept latent in this larger graph, and they are sampled. And what we are searching is the probabilities for sampling these different decisions on the architecture that provide better returns. And at the end of this process, then we read out the best, the final architecture by then doing a last sampling with the learned probabilities. The beauty of doing sampling and working with these probabilities is that space is very well behaved for doing stochastic gradient descent. And then the other thing is, what we are trying to learn here is not a full architecture, but a cell that then is repeated to build the architecture. So we have a number of functional units within that cell, and these functional units are very similar to what we saw with AlexNet, for example. We have an identity unit, a zero unit, a 3x3 depthwise convolution, a dilated convolution, average pooling, max pooling, yeah. And so then, given some training set and a validation set, we train the weights over the training, and then we sample the architecture over the validation, which to me is a little iffy because you are using the validation for training something, but it might work because you are just sampling there rather than training. So once the whole architecture sampler has been trained, as I mentioned, you can read out the final architecture using the probabilities, yes, and also extra assumptions, for example, about the maximum number of connections in each functional unit, yeah. So these cells that are learned, they are plugged into a CFAR architecture or ImageNet architecture. So they are using the same cell for two different problems, yeah. And the CFAR is a simpler one using a convolution, this block, then a reduction cell, these learn blocks, reduction cell, etc. While the ImageNet has a little more convolutions at the beginning. The interesting thing here, yes, is that while they learn these cells that go into these blocks, the reduction cell, on the other hand, is written by hand. And I'm including here the hand design reduction cell because, well, it is pretty in a sense, but also because arriving to this type of reduction cells have taken a lot of human ingenuity and trial and error. So in a way, we have done a network architecture search to arrive here over years, even decades, you can say, of trial and error and gaining insights and deciding what to put where. So to conclude that the future is in this type of things, yes. Instead of building the whole architecture by hand, we will build a scaffolding with maybe some parts that are hand engineered with a lot of ingenuity, and some others that will research using network architecture search techniques. Okay, so to wrap up, complex architectures can achieve complex feature representations if we have a lot of data. And this goes back to the first lecture on the seminar where I was saying that my interest on neural network architectures is the type of complex feature representations that they produce. Now, if you don't have a lot of data, you may want to try transfer learning that can alleviate some of that need for a lot of data. But that implies that there is another model adjacent or in the same domain that you can transfer from. But if you don't have enough data, then simpler system using statistical machine learning and using hand-built features, doing feature engineering will be a good technique, yes. We'll offer the simpler solution to the problem following the Occam razor. So don't forget, I wrote a book on feature engineering, yes. If you are watching this in YouTube, please join us at Discord. My nickname there is Dr. Dav. And finally, I do have this system for tracking papers and paper metadata in a MyMap. And it's particularly useful when you are working in this type of field because it includes full text indexing and query by example, which means that you can take, for example, a draft of a paper you are writing and say, well, which papers that I have read are related to this paper. And that's all what I have. Thank you very much and look forward to the future presentations in the server.